Assalamu alaikum. I welcome you all to another lecture on electrical machines. So previously we have discussed the efficiency of an electrical transformer, where we have studied that the efficiency of a transformer with respect to the loading or the current drawn by the load connected on the secondary side was discussed. So according to that expression, the efficiency of a transformer was dependent on the amount of load connected with it. Now this thing is quite a good parameter of the efficiency of a transformer when it comes to the transformers connected with the fixed load. For example, we have a transformer. Let me draw it. And this transformer is connected with some load, which is a fixed load. And some such fixed loads are usually available in the factory setups, specifically, for example, the textile mills or where different processes happen. There we have this setup where this load is more or less the constant. And therefore, when we discuss about the efficiency, which is equal to X time S cosine theta, and this is X into S cosine theta plus, which is the power factor, plus the P core plus the X square into P copper losses at full load. Now, because this load is a fixed load for a factory setup where a process has to happen throughout the day, probably for almost all the year, and therefore this transformer can be adjusted during the design stage such that we can optimize this denominator for attaining the maximum efficiency. However, if we have a transformer which is actually a distribution transformer, there we have a problem that according to the load profile, according to the nature of the job, nature of the people living there, and according to the school schedule and various other parameters, they actually influence the amount of current drawn from a transformer throughout a day. And therefore, this loading based efficiency of a transformer may not be a very good indication of this efficiency of the efficiency of a transformer. So for this, we use a term that is known as an all day efficiency of a transformer. And this is mostly used when we deal with the domestic distribution transformers, specifically those which you find in your residential areas for supplying different houses and schools like that. So these transformers, they have their secondaries connected with a lot of loads, and the pattern of that load depends on various parameters. For example, there might be during the normal summer and winter, other than the winter vacations, we have the children that are going to school. They may have to turn on the electricity appliances to prepare to iron to press their uniforms, to make the food in the ovens, etc. And therefore, the energy pattern across during that time during which the students have to leave their house for their schools, that is different than the energy pattern drawn from those transformers when the houses are mostly left with the bare minimum number of individuals. And therefore, we need to explain the efficiency of a transformers not in terms of the loading on it, but in terms of the kilowatt hour energy consumed during each day. And for that, we require to have the load profile for a given area. For example, here we have here I have shown the transformer for various different type of houses. For example, this could be a house number 1, this could be house number 2, etc. And we have this house number 3, and this is the house number 4. So there is possibility that the secondary load profile of this given transformer, while it is having connected with the utility supply, they may have, for example, we have this is midnight. Here we have this 6 then we have 8 a.m., then we have 10 a.m., then 12, and then so on and so forth. After this, we have this 5 p.m., and let us say here we have this 9 p.m. here. So it is quite possible that the load is quite minimum, because the people have they might have their appliances on, for example, the air conditioning unit, the lighting load, and the for example, in some cases they might have their electric heaters on for this duration. However, after 6 a.m., there may be an activity during which the students want to go to school. The people who are working people, they want to prepare for their offices. So this actually goes like this, and after 10, when most of them leave for their work, it goes down and goes into a bare minimum till 12, after which there might be some lunch activity or some other stuff, so it goes up again and then it goes down. And after the 5, they may have a spike here because of the activities. People come back to their home, and they might need to charge their electronic appliances. They want to watch some television and other stuff, and therefore this type of a load curve happens for a given utility transformer. So for these type of applications where we have the transformer not connected with a fixed load, there are two things that we need to understand. The first thing is, even if this transformer is working with this load, or with this peak, or with this peak, it always draw some current, ensure the magnetization happening inside the transformer core, and therefore for all kind of loads, the P core losses are there. We cannot disconnect the transformer from supply from the mains just because we have a minimum load available here, because as per the contract, the utility has to supply the consumer with the continuous supply of electricity. However, the copper losses they actually vary with the amount of loading on the secondary winding. So we have all of these switches connected with the system. The transformer secondary current may be operating around its rated value, and therefore it will have some copper losses there. However, during the absence of one or two loads connected with the transformer, we don't have much amount of current flowing here, and therefore the copper losses they will vary. So if we want to analyze this particular thing, we need to understand how much energy is consumed during a 24 hours day, which is usually a very good method of all-day efficiency of a given transformer. So we'll do an example which is given in a famous textbook, and we will solve it for understanding this given concept. Before that, I just need to emphasize here that the efficiency all day is just nothing but the energy output in kilowatt hour divided by the energy which is input to a transformer in kilowatt hour, and we usually do it on at least on one day. However, the seasonal pattern may also be taken into advantage, provided that you have the enough data. However, for most of the cases for a distribution transformer, this 24-hour data provide us enough information to know about the overall efficiency of a given transformer. So for example, we have to find the all-day efficiency of a transformer, which is rated 500 kVA with the full load copper loss equals to 4.5 kilowatt, and the core loss, which is a fixed load, 3.5 kilowatt. Both are at full load. So during the 24 hours, the following is the load profile. So let us draw a load profile here. So this is midnight. Here we have, this is 6 a.m. and then till the 1600 hours, that is equals to 4 o'clock p.m. we have a load, and then till 8 p.m. we have a load, and then again we go to the midnight. So in this scenario, we have a load of 400 kilowatt at 0.8 power factor till from midnight to 6, and then from 6 to to 4 p.m. we have a load equals to 300 kilowatt at a power factor equals to 0.75, and then the load is further decreased to 100 kilowatt, and that is at a power factor of 0.8, after which from 8 to 12 there is no load connected with the given distribution transformer. So in order to solve this given numerical, in order to find out the efficiency of a transformer, we need to know that we need to first convert this load into the apparent power, which is the kVA, and here we have the load at 400 kilowatt, 0.8 power factor, that is equal to 500 volt kilovolt ampere, and the load for 300 kilowatt at the rate of 0.75 power factor, that is equal to 400 kVA, and we have a load which is 100 kilowatt at 0.8 power factor. This corresponds to 125 kVA here. Now, because we should notice that the core losses remain essentially same irrespective of the loading on a given transformer, and therefore the calculation of the core losses is a straightforward process. We will just need to multiply it by 24. However, for the copper losses here, we have the copper loss at the full load. We need to find out the ratio here, and that is equal to 4.5 kilowatt, and the copper loss at 400 kVA rating, that is equal to 4.5 into 400 over 500 square, because it depends on the square of the loading, as we have seen in this given expression. So this becomes equal to 2.88 kilowatt, and then we have the copper loss at 125 kVA, that is equal to 4.5 into 125 over 500 square, and this gives us 0.281 kilowatt here. So the total copper loss here is a sum of all these three, but we need to multiply it by the hours as well. So total copper loss in 24 hours is equal to 4.5 kilowatt, and that is happening for this 6 hours duration from the midnight to 6 a.m. and therefore we just need to multiply it by 6, and then we will add. We have 10 hours long haul for 2.88 kilowatt copper losses, and then we have another 4 hours for 0.281 kilowatt. And for this, because there is no load here, so in this area we don't have any load here, and therefore the copper loss is 0, and therefore we will just write this 4 into 0, and this gives me a total of 56.92 kilowatt hour are the total copper losses in 24 hours, right? So next thing is we need to find out what is the total core loss in 24 hours. This is equal to 24 times the core loss is defined as 3.5 kilowatt. So we'll multiply it by 3.5 kilowatt, and this gives me equals to 84 kilowatt hour here. So now the total losses in this given example are, total losses is equal to 56.92 plus 84, and that is equal to 140.924 kilowatt hours. So now we can find out the efficiency here simply by dividing these output divided by the output plus the losses, and that will give us the efficiency here. We can also write this in terms of 400 into 6 plus 10 into 300 plus 4 into 100 divided by 400 into 6 plus 10 into 300 plus 4 into 100 plus 84 plus 56.92, and this all is in kilowatt, and therefore we get an efficiency equal to 0.976, or that is equal to 97.9%. 97.6% is the efficiency. Instead of having it concentrated on a given one point, rather than that, we expand the operation region, and thereby we calculate the total efficiency of a given transformer. So that's all for today. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.